Welcome back to MP2. So now it gets real. And we start talking about the cardiovascular system. We're going to start by talking about the blood vessels. So to begin with, the cardiovascular system is obviously designed to transport blood through the body. It includes the heart, the blood vessels, and we've already discussed blood functions here, transporting stuff to and from everything in the body. This is all you're probably aware of, so we're not going to spend a lot of time rehashing this. Now, we've got the blood vessels. This is going to begin and end at the heart. It makes a continuous circuit. Here are the rules. Arteries always carry blood, arteries always carry blood away from the heart. Typically, that is oxygenated or high oxygen blood. Not always, but usually. Pulmonary circulation, which we'll look at later, is a little different, and fetal circulation is its own situation. Veins. Veins carry blood back to the heart. Always. Now, again, typically that would be low oxygen blood, deoxygenated. Not always the case. Again, the exception there would be your pulmonary circulation and umbilical vessels, but we'll talk about capillaries are the exchange vessels, the ones that are actually in contact with the tissues, the ones that are going to deliver the blood and the resources the blood brings with it to the tissues. Here we have this nice little chart. We have the heart, which in this figure does not look like a heart, arteries, in red, capillaries here in purplish blue. Now, notice in green you have your lymphatics, a one-way system that drains that excess fluid, which we talked about previously. Now, again, arteries carry blood away from the heart, and the smallest branches of those arteries are arterioles. These will be more important for vasoconstriction and vasodilation. Capillaries, the smallest of the blood vessels, bigger arteries through here and then smaller arteries down there. Come back to the other side of the venules, the smallest veins, and then veins. There are different layers of tissues here. We have the tunica, intima, media, and externa. So the inner, middle, and external layers. We have a hollow organ, and this does include the blood vessels. Hollow place is called the lumen. So the lumen of the blood vessels, where we would find blood. Once we get down to the level of capillaries, all that exists is the tunica intima, the innermost layer. But let's look at that. Here we see arteries and veins. The artery side, we've got the tunica intima, just this inner layer of these sort of pink endothelial cells here. Now this is simple squamous cells. They're endothelium, one cell thick. That's the innermost layer, and it is continuous through all the blood vessels. Notice that down here in the capillary, that's all that exists. The capillary does not get those other layers of tissue, which makes perfect sense because the capillaries are exchange vessels where oxygen and carbon dioxide have to move in and out of the blood. Much easier to move things in and out of the blood if the barrier between the blood and outside the bloodstream is one cell thick. We look at the artery over here, you've got that one cell, but then you've got the subendothelial layer and the internal elastic lamina, the smooth muscle, the external elastic lamina, then the collagen fibers that surround that, and maybe even like more blood vessels, the vasa vasorum out here. You've got multiple layers of cells and tissues to go through. Yeah, nothing's diffusing through. But down here, where there's just one cell to get through, now we can move stuff in and out. So capillaries are the exchange vessels, and they're very, very thin to allow that. So the tunica intima is the endothelium that lines all the blood vessels. The tunica media, smooth muscles, some elastic fibers. The tunica externa, the outer collagen layer. Bigger blood vessels actually have something called the vasa vasorum, which is the blood vessel for the blood vessel. And you can see that in that prior drawing, where those blood vessels are in that tunica externa to take care of those tissues. Here's a nice little chart. You see the big, fat, elastic arteries there. Lots of smooth muscle, lots of elastic tissue. Notice that as we go through these vessels, the endothelium layer, that first bar on the graph, is constant. Because it is. It's constant through all the blood vessels. While the amount of elastic tissue and smooth muscle and collagenous tissues on the outside may change, that amount of endothelial tissue on the inner layer remains constant. So there's your big fat elastic arteries, muscular arteries, the smaller arterioles. Go down to the capillary where we just have that endothelium, and then venules and veins. One other thing to notice with the difference between veins and arteries is the arteries have a lot more elastic tissue there. The arteries are stretchier. In dissection, the arteries, the big arteries kind of feel like surgical tubing, and they're kind of stretchy and elastic. The veins are just kind of floppy. They don't have that structure, that elasticity to them. So the big arteries, really big, thick arteries, elastic. And that elasticity will be important later. This includes the aorta and the major branches. Arteries are pressure reservoirs. Here's where that elasticity comes into play. When blood is pumped out into these arteries, it stretches them. And anytime you stretch something that's elastic, it's going to rebound back into its original. In terms of the artery, that rebound continues to shove blood through the bloodstream. So when you blow up a balloon and then let it go, the air escapes because the elasticity of the balloon contracts and it pulls that balloon back into its original shape and it shoves the air out. When you push blood out into an artery, it stretches that artery out, and then when the artery rebounds, it shoves the blood out further down the line. So arteries are pressure reservoirs. The muscular arteries as we go out, this is going to be important for vasoconstriction. There's more proportional to the muscle here. The arterioles are the smallest of the arteries. They're going to lead directly into capillaries, and thereby they control blood flow into capillaries. Capillaries are the exchange vessels, microscopic vessels. You can't see capillaries in dissection. They are one cell thick. They're so tiny that red blood cells have to line up single file to go through. These little stacks of cells. The fact that they're only one cell thick also makes them very fragile and very susceptible to pressure change. Add more pressure to a capillary bed and it will rupture. This is problematic in the kidneys. When I taught at another university, which I won't name here, often after a football game, my students would come in and their face would look like they had a red raccoon mask around their eyes. Not sunburn, caused by vomiting after a weekend of excessive drinking. This forceful vomiting increased the pressure in the capillaries in their face as they vomited and caused those capillaries to rupture, which with this sort of red raccoon mask. Looks like you just sunburned. that pattern around your eyes. We find capillaries in all the tissues except for cartilage. Remember back last semester, cartilage is avascular. Epithelial tissue is avascular. The cornea and the lens of the eye are avascular. And that should be pretty obvious. If they weren't, you'd see blood all the time. Now, there are three structural types of capillaries: continuous, fenestrated, and sinusoidal. Continuous capillaries are the most common capillary. They're also the least permeable. The cells are held together by tight junctions, so it's a little difficult to get stuff in between the cells. There are some gaps, we call them intercellular clefts, that let stuff out. In the brain, however, those tight junctions are pretty complete, and that's what makes up the blood-brain barrier. Here's our tight junctions. If you're in the bloodstream and you want to get out, you've got to go through these intercellular clefts. Fenestrated means it has holes in it. And some of these cells will have holes in them. We find them in places for filtration or absorption, like the small intestine. So there's a fenestrated capillary. The most permeable capillary and the least common is the sinusoidal capillary. Forget tight junctions. There's fenestrations. There's a bunch of tiny holes. There's also gigantic holes in between the cells. We're not even trying anymore. Cells can get in and out. Red blood cells go in, red blood cells go out. And we find these in places where we want red blood cells to go in and out. The liver, or the spleen, or the bone marrow. So there's a sinusoidal capillary. Giant holes. Capillary beds are these networks of capillaries between the arterioles and the venules. There is a straight shot. You can go straight from artery to vein. It's called a vascular shunt. Most of the time, however, blood will be routed out in this network of capillaries between the veins and arteries. And that would be what we call a true capillary. Blood flow is controlled through capillaries. So here's the thing. Blood flow through capillaries is intermittent. You actually don't have enough blood in your body to fill all the capillaries simultaneously. And your tissues don't need constant resupply of oxygen. Your skin, for instance, your skin doesn't have an incredibly high metabolic rate. You don't have to constantly be delivering nutrients to your skin. It's not burning calories, just sitting there being skin. So it's not necessary to have this constant flow like your heart and your brain have. So blood flow out to those tissues is regulated by these things, these tiny little muscles called precapillary sphincters. So there we see our straight shot, that vascular shunt, and then we see these little muscles there that control flow out into this true capillary bed, so that often blood is going to go straight through. It doesn't have to go out into that exchange portion. Capillary comes back. We have venules. Venules still pretty porous, and they combine together in the veins, and veins bring blood back to the heart. Arteries are pressure reservoirs. Veins are blood reservoirs. At any given time, about 65% of the blood in your body is in the veins. So arteries, and this is important, arteries are high pressure, low volume. Veins are high volume, low pressure. One more time. Arteries, high pressure, low volume. Veins, high volume, low pressure. Okay. When we look at the walls of the arteries and veins, you can definitely see a difference. The lumen of that vein is gigantic. The wall is super thin. The wall of that artery is really thick and elastic and stretchy. The lumen is much smaller. Here's another view of the vein and the artery in cross section. Here is where blood is found in the venules, in the arteries, and then pulmonary heart capillaries. Now, veins are low pressure but high volume. Big rule, important thing. Fluids move with a gradient, a pressure gradient, meaning that fluids move from high to low pressure. It's blood pressure that makes circulation work. Pressure is highest at the aorta and lowest at the vena cava. So blood wants to go the direction that it's going. But in the veins, there's not a lot of pressure. So how do we get blood back? Well, we try to resist blood flow as little as possible, so veins are really big and floppy. And we have valves in the veins to prevent blood from backflowing, so that as blood gets pushed back up toward the heart, it can't go back down. Here is a picture of this valve in the vein. So when you walk, the calf muscle there squeezes that vein like so, and blood can't go down. It has to go up, so it gets shoved up toward the heart. In fact, skeletal muscle contraction is one of the major ways that we assist the veins. Walking, moving, even breathing, those pressure changes in the chest squeeze the veins and kind of milk blood back toward the heart. A friend of mine is a pharmacist, and he stands all day long. And what he found was that standing still all day long very quickly led to varicose veins. And a varicose vein is when we have a failure of that valve. When blood pulls in that vein and stretches it out, it's not really elastic, so it gets all stretched and distended, and then you have the varicose vein. An anastomosis is an alternate route through circulation, a collateral channel. It branches off blood vessels so that there's more than one route to take. Veins are great at anastomoses. Lymphatics anastomose like crazy. All right, so now some more. Blood flow. The term blood flow, the amount of blood that's going through a vessel, an organ, or even the whole body in a period of time. Milliliters per minute. Talking about the whole system, that's cardiac output, or how much blood the heart's pumping out. At rest, blood flow is pretty constant. But blood flow varies a lot through individual organs. For individual organs, blood flow is based on need. So when your muscles need more blood, they get more blood. When your stomach needs more blood, it gets more blood, etc. Blood pressure is obviously the pressure that's exerted by the blood on the blood vessel. That pressure gradient is why blood moves. High to low pressure. If there's no pressure, blood's not moving. Resistance is always the opposition to flow. In essence, it's friction. The more resistance you have, the less blood flow you get. And in terms of blood, there are three sources of resistance, three things working against blood flow. The first of them is viscosity. Viscosity is how thick the blood is. The thicker your blood is, the more resistant you encounter, the harder it is to get blood to move. The other thing, another source of resistance here, is the length of the blood vessel. The longer the blood vessel is, the more resistance you encounter along the way. Those things are pretty constant, though. They're not really super easy to change. When your body needs to alter pressure, or the pressure gradient, it changes the diameter of the blood vessel. So, if you make the blood vessel bigger, you decrease resistance. The bigger the vessel, the less resistance. Hold on. So, we find most resistant smaller diameter arterioles. We can change this as we need to. We can increase and decrease resistance. And because we can increase and decrease resistance, we can increase and decrease blood flow, because resistance is to some degree based on the blood vessel. So if you're interested in the math, here it is. Blood flow is directly proportional to the pressure gradient. So the difference between pressure on either side, the bigger the gradient is, the faster blood's going, or the more blood flow you get. Blood flow is inversely proportional to resistance. So if resistance increases, blood flow decreases. Resistance is the important thing, because we easily change the diameter of blood vessels. It's a lot more difficult to change the thickness of your blood. It's a lot more difficult to change the length of a blood vessel. But the diameter, we can. Systemic blood pressure is the pressure for the system. Pressure is measured millimeters of mercury. And you'll find that it's highest in the aorta, and it drops as you go through. There's a nice little graph that shows blood pressure. That pressure in the arteries shows us two things. One, that they're elastic, and two, that the heart is pumping blood in. And you can see they're both. When we measure blood pressure, we get systolic and diastolic. Systolic pressure is the pressure that's exerted when the heart contracts, and diastolic is the pressure that's still there when the heart's not contracting. If you ever hear the term pulse pressure, that's the difference between the mean arterial pressure. So the average blood pressure, hence the term mean, the average blood pressure in all the arteries, it's the pressure that's blood out. There's the math for it. The diastolic plus 1/3 the pressure. You'll find that they both drop as you get further away from the heart. In the capillaries, pressures drops. Why? Because if you don't drop the pressure before you get there, the capillary is going to freaking explode. It doesn't take a lot of pressure to force fluid out. Well, oh, my picture's a little too far back. But there's just a lot of capillary. There's a lot of spread there for those capillaries. Right, so we don't want to rupture the capillary. Venous pressure, there's not a lot of pressure here. We don't have a lot of gradient. It's not necessary. We've got the valves and things to keep blood going back to the heart. Like I said, in the chest, as you breathe, it squeezes the veins. As you move, the skeletal muscles squeeze the veins. And bigger veins you have some vasoconstriction there, but mostly we've got these sort of pumps where we're squeezing the veins, and then those valves prevent the backflow of blood. Here's another great little view of those valves. As that muscle contracts, blood has to go back to the heart when those veins are squeezed. Blood pressure, again, is the thing that makes circulation happen. Maintenance of blood pressure is something we super care about because it requires this coordination of these different organs with the supervision of the brain. The three big things that influence blood pressure: cardiac output, resistance, and volume. This is very easy. This makes perfect sense. Here's the math if you really care. So let's translate from math to English. Cardiac output, resistance, and volume. Cardiac output is how much blood your heart's pumping out. The more blood your heart pumps out, the more pressure you have. Perfect sense. Peripheral resistance. That's the opposition to blood flow. The more resistance you have, the more pressure you have. Think about resistance. Think about sticking your thumb over the end of the water hose. That's resistance. And when you put your thumb over the end of the water hose, what happens to the pressure on that water coming out? It goes up. Increase resistance. The last thing there is volume. The more volume you have, the more pressure you have. So as volume goes up, the pressure of this fluid goes up. So those are our factors for blood pressure. Cardiac output is determined by different things. We're going to ignore some of these terms like ESV right now. More on cardiac output numbers and look at how cardiac output, stroke volume, these in systolic and diastolic volume. Right now, I'm not concerned with this. Here's this, all equations of, we'll come back. For short-term control of blood pressure, we change resistance. All we have to do is dilate or constrict blood vessels. Resistance changed, blood pressure changed. Long-term control of blood pressure is done by controlling blood volume. All right. All right, we're back. All right. Let's help you make sense of this. Let's talk about something we use as a pharmaceutical to lower your blood pressure. Also often prescribed a diuretic. What is a diuretic? Well, a diuretic makes you pee more. The more urine you put out, the more water you lose. Diuretic causes decreased volume. And if you decrease volume, you decrease pressure. That's long-term regulation. Long-term regulation of blood pressure is the job of renal regulation. Short-term regulation of blood pressure, the brain, some hormones. Long-term regulation, that's the kidneys. So again, the brain will maintain pressure by changing the diameter of blood vessels. This can involve different reflex arcs. We're not going to get into baroreceptors and vasomotor things. There are pressure receptors that protect blood flow to the brain. Baroreceptors, that's what that is. And then we have the vasomotor center in the medulla. So this is all short-term control of blood pressure. And we'll blow through this pretty quick. Not really worried about that. Chemoreceptors are more important for respiration than they are for blood pressure. Higher brain centers, you can change your blood pressure with higher brain stuff. So like when you get pissed off, your blood pressure goes up. Right? When you relax, your blood pressure comes down. So you do have some cortical control of that from the thalamus and the cerebral cortex. Norepinephrine and epinephrine cause increased cardiac output because your heart beats faster, more in a bit. And then we have big picture hormone, angiotensin 2. All right, here we go. Last semester in AMP1, we talked about your brain, right? Your brain is the worst girlfriend you ever had. Very self-centered. It demands a lot of resources. It's obsessed with your friend, right? It stalks you, and it'll kill you if you screw up. Terrible thing with your kidneys, however, are type A. They're workaholics. Your kidneys are that guy that's in this class that gets mad when he makes a 99. Why didn't he get 100? Kidneys are super obsessed with their job. What is the job of the kidneys? To filter your blood. How does that work? Well, you got to put some pressure on the blood and force it through a filter. Okay, so if at any point the kidneys feel like they can't do that, they release something called renin. And this sets off what's called the renin-angiotensin mechanism. The renin-angiotensin mechanism is a big picture blood pressure control mechanism. How does it work? Well, in the plasma, we have a protein, angio. Oh man, sorry, I screwed that up. I don't know how to erase. So, here, angiotensinogen. But there's that suffix again that always means an inactive protein. Angiotensinogen in the plasma. Right? Inactive protein in the plasma. When the kidneys release renin there, it turns angiotensinogen into angiotensin 1. Who cares? No one freaking cares. Angiotensin 1 gets converted into angiotensin 2. Now we care. Now the enzyme that does this is called ACE. ACE stands for angiotensin converting enzyme. Hey, well, what it does, it converts angiotensin 1 into angiotensin 2. Angiotensin 2 do? Well, angiotensin 2 is a serious hormone. Well, angiotensin 2, vasoconstrictor. It means it makes your blood vessels constrict. Now, we constrict your blood vessels, we're going to increase resistance, which means we're going to increase pressure. Still with me? Back a few slides if you're not. Increasing resistance means that we increase pressure. What else is angiotensin going to do? It's going to cause the release of aldosterone. Aldosterone is salt-retaining hormone. You retain sodium. And if you retain sodium, what else do you retain? Water. And if you retain water, you're increasing volume. And if you increase volume, you increase pressure as well. So now we increase resistance, we increase volume. Both of those things increase blood pressure. Angiotensin II, then its function is to raise your blood pressure. Does that very well. Now we do have some other hormones. We have atrial natriuretic peptide from the heart. Atrial natriuretic peptide kind of does the opposite of aldosterone. You put sodium in the urine, you lose volume. Antidiuretic hormone. Antidiuretic. Antidiuretic hormone can cause vasoconstriction if your blood pressure is going down. This is a Hail Mary pass by your body. If you're bleeding to death, right, you just drop a crap load of ADH in the system, and maybe your blood vessels will constrict enough circulation working. Probably not. You're dead. Never mind. All right. So those short-term things you adapt to very quickly. So it's the kidney's job to manage this. Now, in its management, there are two things that are going on here. One is very simple. It's called the direct renal mechanism. Screw hormones and all this heart crap. It's just physics. The higher your blood pressure is, the more urine you make, because you force more blood through the kidneys. If you make more urine, you decrease volume, you decrease pressure, problem solved. If your blood pressure is not high enough, you don't make as much urine. You retain water, your blood pressure goes back up, problem solved. The indirect mechanism is what I just talked about and squeezed in on a slide when I had it slides later, where we have the release of renin and angiotensin II. So that's going to increase volume, antidiuretic hormone. That's going to increase volume. That's going to increase resistance. All of those things increase blood pressure or make people to do their job. So now, your next that you should look at will be the heart.